you just learned how to compute the over-barrier reflection coefficients in semi-classical approximation. Let me remind you the brief details of what just been done. So you consider the case where the equation for turning points has no real solution for x. And naturally, you found the turning point in the complex plane of your coordinate x. And the idea was to solve the corresponding Schrödinger equation in the vicinity of this turning point and match it with the correct semi-classical solutions. And then go back on the real axis of x. And this way, we are able to recover the reflection and transmission amplitudes. Now, but this was the simplest case. However, there are potential, and they are quite frequent in quantum mechanics, which have several turning points in the complex plane. Sometimes even infinite amount of turning points, and this case correspond to their crystal symmetry of the periodic potential. Here, for now, we address the simplest case when there are two turning points. And then following this principle, you can actually generalize this consideration on the case of 3 or more turning points. Right. So suppose now there are two turning points in the complex plane of x, and the question is, how do you compute the corresponding reflection coefficient this time? Let's split our complex plane in 3 regions. In the right region, due to our search for scattering event, we expect that in the region 1, you have just transmitted wave. Now, as you remember, we can solve the Schrödinger equation in the vicinity of this x0 point, and the result is that here, to the left of this x0 point, we have their incident wave and reflected wave. And we can actually write down the corresponding amplitudes, match them with semi-classical ones, and here they are. The amplitude in region 1 is as follows. And the amplitude in region 2 in their vicinity of this point x0, actually not in the, but just in complex plane here, it just represented by the sum of their incoming incident wave and the reflected wave, and they have the same amplitude, which is a striking feature of this consideration in a complex plane, because when we return to the real plane, then the amplitude change, and actually their reflected amplitude acquires the corresponding exponentially small prefactor. But in the complex plane, they are identical. Right, so now since we know our consideration assume that there is a semi-classical evolution from x0 point to point x1, we expect the same kind of behavior of the solution between these 2 points up to the vicinity of point x1. Well, and from the mathematical theory, we know that there are 3 anti-Stokes lines in the vicinity of each point. They are inclined by angle 120 degrees centigrade. And naturally, we expect that there is a single anti-Stokes line which connects the 2 points. Right. Let's figure out what's happening with both of these waves in the vicinity of the turning point x1. It will be your homework to show that the reflected wave is turned again into the reflected wave when we turn to region 3. So there is no reappearance of the wave with plus sign. However, the transmitted wave, this one, which propagates to the right, is again due to the standard procedure is turned into the combination of the incident wave and a reflected wave in region 3. So this exponential becomes the same one and acquires additional factor with minus with the same expansion with minus integral. However, but this is true, of course, in the vicinity of point x1. So to simplify things, let's actually split these semi-classical integrals in the exponents in the following manner. The integral from x0 to x is split into the integral from x0 to x1 plus the integral from x1 to x. And we rewrite this solution in the following fashion. We introduce the semi-classical phase, which is an integral from x0 to x1. Let's denote it as 0, 1. And the solution in region 2 is rewritten as follows. Now, according to our general rule, when the transmitted wave, which corresponds to this plus sign exponential, is transformed into the combination of the incident exponential and the reflected one, with the corresponding additional phase. So in the end, when we turn to region 3, there are two reflected waves. One comes from turning point x0, which goes untouched through region 2 and arrives at region 3. Here it is. And the other one, which appears when we continue our solution, which corresponds to outgoing wave to from region 2 to region 3. So here they are, the second reflected wave and the first reflected wave. So in the end, the solution in region 3 can be written as follows. Let's factor out this exponent exponential e to I as 0, 1. Right. And here we go. The incident wave and the combined transmitted wave, which is one plus e to into minus 2i as 0, 1 multiplied by e to minus I pi by 2. Right. And our final step is to, and I forgot to add the corresponding negative sign exponential. And our last step is to return these exponentials or these exponents onto the real axis x. So we do this with the following simple trick. We choose some point, I don't know, x2 on the real axis. And well, suppose the potential function decays at plus and minus infinity, and the momentum asymptotically is turned into momentum p minus here at minus infinity. So we split this integral into the integral from pi p minus from x1 to x dx plus p minus x minus x1. Oh, sorry, we don't actually need this additional point x2. And so since we have this p minus, we expect that since p tends to p minus at minus infinity, when x tends to minus infinity, we expect that this integral converges, and at large negative values of x at minus infinity, we can substitute the upper limit with minus infinity, because we expect that this limit actually exists, and this integral is turned into some finite number. So our semi-classical phase now is represented as a standard asymptotic p minus x, which is just a plane wave, plus some number which we denote minus phi naught. So in the end, our wave in region 3 now looks as follows. We can factor out now this phase minus phi naught from all our exponents, and what we get is the following thing. And from this final expression, we can easily extract their correct scattering reflection amplitude. So here it is, basically. It's so this is minus I pi by 2 with purely imaginary factor, which is irrelevant. However, this phase phi 0, in general, it contains their non-zero imaginary part. That is why when we compute their reflection coefficient, which is given by this modulus squared of the reflection amplitude, this phase phi naught can contribute actually to the final reflection coefficient. And here it is. So now we arrive at the final answer. So the reflection coefficient, as in the case of single turning point, it's just e to minus 4 imaginary part of phase phi naught multiplied by the modulus of this complex expression squared. And this is our final answer for the reflection coefficient in the case of two turning points. And here comes some comments. Well, first of all, you see the appearance of this in general oscillating expression. Indeed, our phase S01 usually it's semi-classical phase, which is large. And so basically we have here in our square braces their oscillating expression. Otherwise, the prefactor is identical to the one which you get from the theory of scattering from the single turning point. So what next? Well, the other comment is that we considered the case of the scattering where both points x0 and x1 well separated. What does that mean? That means that their evolution from between point x0 and x1, according to Schrödinger equation, is a semi-classical one. So the corresponding semi-classical phase is assumed to be large. Only in this case, this whole consideration is relevant. If you have both turning points which are closer to each other than, for example, their wavelength of the incoming particle, then all this consideration is, of course, irrelevant, and you should treat the problem in a different manner.